Assalamualaikum and hi everyone, my name is Muhammad Iqbal Misharuddin, my metric number B1325200017. Today our group here to present our experimental finding on bell friction. Bell drive systems are widely utilized in various mechanical applications, ranging from automotive engine to heavy industrial machinery, primarily as a means on transmitting power between shafts. While these systems are essential for industrial operation, they are governed by specific mechanical principles that dictate their efficiency and reliability. The core of our study focus on understanding how frictional force, which are often considered a challenge in many mechanical systems, are actually harnessed to facilitate effective power transmission. By investigating the interaction between bell and pulley, we aim to gain a deeper insight into the factors that influence performance, such as material properties and contact geometry. The experiment bridged the gap between theoretical mechanics and real-world engineering, allowing us to evaluate how we can optimize power transmission system to ensure they operate at peak efficiency while minimizing energy loss and mechanical wear. Context in mind, our experiment is guided by three main objectives that serve as the foundation of our analysis. The primary objective of this experiment is to explore the fundamental principle of mechanical power transmission with a specific focus on the influence of the right angle on frictional force within a bell system. Through this experiment, we aim to demonstrate empirically that the magnitude of the frictional force generated is significantly dependent on the extent of the contact area between the belt and the pulley. By analyzing this relationship, we can understand how increasing the right angle enables the system to maintain the necessary tension to transmit power efficiently without mechanical failure caused by slippage, which is a common source of energy loss in industrial machinery. Furthermore, this experiment aimed to determine and evaluate the coefficient of friction for various combinations of bell and pulley material, such as the interaction between rubber and grey cast iron or leather and grey cast iron. The determination of this coefficient is critical in engineering as it serves as a fundamental parameter that dictates the gripping efficiency between two contacting surfaces. By comparing our experimental results against established theoretical values, we can assess the impact of surface roughness and material elasticity on overall system performance, which subsequently assists engineers in making informed decisions regarding material selection for specific power transmission application. The final and most technical objective is to validate the accuracy of the Euler-Etelwin formula expressed as T2 equal to T1 exponent coefficient of friction angle, which serves as the theoretical foundation for belt friction in engineering mechanics. Through this experiment, we aim to verify the exponential relationship between the ratio of the tension on the tight side T2 to tension on the slack side T1 with respect to the coefficient of friction and the right angle. By conducting tests under various loading conditions, we can measure the correlation between theoretical prediction and experimental data, thereby confirming the reliability of this formula as a predictive tool for designing safe and durable power transmission system. Collectively, the achievement of this objective provides a comprehensive understanding of how basic physical theories are integrated with practical application to minimize wear, reduce slippage, and optimize energy transfer efficiency in complex mechanical systems. Now we move to the next part, which is justification of solution explained by Syed Harun. That's all from me. Thank you.
Hi, my name is Syed Harun bin Syed Abdul Halim. I'm with my matrix number B1323105777. And now I would like to explain the justification of our solution for this belt friction experiment. The solution chosen for this experiment is based on the Euler-Etelwin equation, which is a fundamental theory used in mechanical engineering to describe the relationship between belt tension, friction coefficient, and rep angle. This equation helps us understand how force is transmitted between a belt and pulley systems and why friction is important in preventing belt slippage. The reason for using this approach is that the belt-driven systems are widely used in industrial machines, conveyors, automotive applications, and power transmission equipment. If there is insufficient friction between the belt and pulley, the belt may slip, resulting in energy loss, reduced efficiency, and increased wear of mechanical components. Therefore, understanding the relationship between friction and rep angle is essential for designing reliable and efficient belt drive systems. In this experiment, We validate the Euler-Atherwind equation by measuring the tension on both sides of the belt under different rep angles and loading conditions. By comparing the experimental results with theoretical calculations, we can determine whether the equation accurately predicts the behavior of the belt systems. Another justification for this solution is that it allows us to evaluate different combinations of belt and pulley materials. Different materials have different coefficient of friction, which directly affect the ability of the belt to transmit power. Through this investigation, we can identify which material combinations provide better performance and reduce the risk of slippage. Furthermore, the results help engineers select appropriate belt materials, pulley materials, and tensioning methods for practical applications. Proper belt tensioning not only improves power transmission efficiency, but also reduces mechanical wear, extends equipment lifespan, and lower maintenance costs. Therefore, the Euler-Atherwind equation provides a practical and effective solution for analyzing belt friction behavior and improving the performance, reliability, and efficiency of belt-driven mechanical systems. That's all from me. Thank you.
Assalamualaikum and hi. My name is Muhammad Azam Akra. My matrix number is B13252010. Okay, so my part is methodology. First, set up the belt friction apparatus. First, the belt friction apparatus was set up using the selected pulley and belt material. This was done to create a suitable system for studying the frictional behavior between the belt and the pulley. Second is apply a tension and measure holding force. Next, tension was applied to one end of the belt known as T1. The holding force T2 was the measure when the belt was about to slip. These values were used to calculate the tension ratio and the coefficient of friction. For example, if T1 is 60 Newton and T1 is 40 Newton, the tension ratio is 1.5. Third is vary the rep angle and load. After that, the rep angle and the applied load were varied to observe their effect on frictional resistance. This helps us understand the relationship between the rep angle and the friction force. Example, based on experiment result, when the rep angle increased from 30 to 180, the tension ratio also increased. This indicates that friction increased as the rep angle become larger. Conclusion of methodology. In summary, this experiment was conducted by measuring the belt tension at different rep angle to study the relationship between rep angle, tension ratio, and coefficient of friction.
Hello, myself Nangani, son of Rajendran. Next, I will explain the result and discussion of our belt friction experiment. From this experiment, we observed that when the angle of rub increase, the tension ratio between tight slide and slack slide of the belt also increased. This happened because the larger content between the belt and pulley created more frictional resistance, allowing the belt to transmit higher force without slipping. Based on the experiment data, the calculated coefficient of the friction varies depending on the belt material used. Different material produce different friction value because surface roughness and material properties affect the grip between the belt and pulley. This experiment coefficient of the friction was the compared with the theoretical value. The difference between both value may be caused by factor such as a measurement error, belt tension variation, and slight slipping during the experiment. Overall, the result proved that the value equation is valid, where the belt tension ratio increase exponentially with the angle of rub. Proper belt selection, the tension adjustment are important to improve the power of efficiency to reduce mechanical slip. So that's all from me. Thank you.
Assalamualaikum and good morning. My name is Muhammad Haris Akmal bin Hazlan and my metric number is
B1325200015. So to bring this presentation to a close, our experiment provides a comprehensive valuation of the principle governing belt friction. Firstly, our experimental result clearly demonstrate that frictional resistance does not increase linearly but rather exponentially with the wrap angle, which serves as a practical confirmation of the Euler-Etelwine formula. Secondly, our comparative analysis as shown in the data table highlight how material selection, such as using different combination of leather, ham or rubber on grey cast iron, significantly impact the limiting tension ratio. This finding underscore the vital role that material elasticity and surface properties play in the overall efficiency of mechanical drive system. Ultimately, the key takeaway from this study is that mechanical design require a precise balance between geometric parameters, specifically the wrap angle, and the physical properties of the material used. We have concluded that proper belt tension is not merely a maintenance task, but a critical engineering requirement to effectively minimize mechanical slip and maximize energy transfer efficiency across the entire system. That concludes our presentation. Thank you.